Okay, so now that we know any linear transformation can be written as a matrix transformation, let's take a look at some examples about how we can do this and think about how we can actually interpret these maps. So let's first consider the linear transformation T, which is going from R2 into R2, which takes, this is a vector X, so this has an X1, X2, and maps it to 1/2 times vector X. Okay, so these are bold fonted X's, just keep that in mind. So these are pairs, X1, X2 is being mapped to 0.5 times the pair X1, X2. So let's find the standard matrix A to represent this linear transformation. And so in order to construct that matrix, we just need to know where the two standard column vectors get mapped to. So if I were to map the first vector, column vector 1, 0, right, that gets multiplied by 0.5. So multiplying the scalar 0.5 times the vector 1, 0 would give us the vector 1/2, 0. Similarly, the image of E2, standard column vector 2, that would be 1/2 times 0. And then down here, we would get 1/2 times 1. So that gives us the vector 0, 1/2. So now that I know where E1 goes and I know where E2 goes, that's all we need to come up with the matrix A. So the first column of A is going to be the image of E1. That's where this comes from. And the second column of A would be the image of E2. And so that's where this second column comes from. So we have what we would call here a diagonal matrix where the values on the diagonal are equal to 1/2. So let's see what this transformation is actually doing in R2. So this has a very geometric interpretation. We're mapping points in R2 to other points in R2. So to motivate what's happening here, we'll consider elephants. So here's a photo that I took a number of years ago. I was lucky enough to work in vacation in Botswana. So here's a nice photo of a mama elephant and the baby elephant. So let's consider just one elephant over here that we have in blue. So let's say here's where we're starting in R2. Let's see, well, what effect does this map T have on this space? So notice that this vector 1, 0, and this vector 0, 1, we can write right over here. So this would be the vector 1, 0, and here's the vector 0, 1. So this is E2, and this is E1. And under this map, we know where these vectors go. Namely, this vector E1 goes to 1/2, 0. So it winds up right here. And this vector E2, which was 0, 1, it winds up over here at its image, which is 0, 1/2. So every vector in R2 is getting dilated, is getting contracted, right, by a factor of 1/2. So every single vector is getting contracted by the same factor. So what's happening is this elephant is shrinking. We would call this map a dilation map. So this linear transformation does have some really useful applications in computer graphics and things like this. So here we have a dilation of this elephant. It looks the same scale-wise. We've just scaled it down by a factor of 1/2.